Push the book harder, yet it slows down. Why does more force make it drag? The invisible hand of kinetic friction fights every inch of motion. It's not magic, just physics. But how can resistance grow as the book slides? The table's roughness and the book's weight set the stage. Every micro scrape turns motion into heat. Yet the force stays steady until the book stops. How does a constant push meet a changing speed? The book sits on a flat wooden table. Gravity pulls it straight down. The table pushes back with the same force. This is the normal reaction. When you slide the book, another force appears. Kinetic friction. It points opposite to motion and resists every step. Its magnitude depends only on how hard the surfaces press together and the roughness of the wood. On a smooth hardwood surface, μk lies between about 0.20 and 0.30. A heavier book increases normal load in step, so friction grows. Lighter books feel less resistance and slide farther. The book sits on a flat wooden table. Gravity pulls it straight down. The table pushes back with the same force. This is the normal reaction. When you slide the book, another force appears. Kinetic friction. It points opposite to motion and resists every step. Its magnitude depends only on how hard the surfaces press together and the roughness of the wood. On a smooth hardwood surface, μk lies between about 0.20 and 0.30. A heavier book increases normal load in step, so friction grows. Lighter books feel less resistance and slide farther. Slows the book until it stops or you increase your push. Pause 0.8. The book rests on a flat wooden table. Gravity pulls it downward, represented by a red arrow. An equal upward force from the table balances this pull. This upward push is called the normal reaction. Because the surface is horizontal, the normal equals the book's weight. When you slide the book, a new force appears. Kinetic friction acts opposite to the direction of motion. It points leftward if the book moves rightward across the table. The magnitude of kinetic friction depends on the coefficient and normal force. On a wooden surface, this coefficient is relatively small, thus the book slides smoothly once pushed. If you increase the push, the friction stays constant until motion stops. Pause 0.8. When a book slides across a wooden table, the force that resists its motion is called kinetic friction. This resisting force equals the product of the coefficient μk and the normal force pressing the book onto the surface. Because the normal force on a flat table is simply the weight, kinetic friction scales directly with how heavy the book is. For typical hardwood surfaces, μk lies between about 0.20 and 0.30 when both contact materials are wood. These values come from laboratory measurements that vary with surface finish and moisture. If the book is heavier, the normal force increases proportionally, so kinetic friction grows in step. Conversely, a lighter book experiences less resisting force and slides more easily. The proportionality constant μk is independent of the sliding speed for moderate velocities. Thus, by measuring how far a book travels before stopping, one can estimate μk if the mass and table height are known. This simple experiment illustrates the core idea that kinetic friction is a force proportional to normal load. Pause 0.8. A book slides across a wooden table at first high speed. Kinetic friction acts opposite to the motion, pulling back on the book. This opposing force does negative work on the moving book. Negative work means energy is removed from the book's kinetic pool. The lost energy appears as microscopic heat in the wood and air. As heat rises, the book's speed steadily drops over time. On a velocity time graph, this drop looks like an exponential curve. Each tick of the graph shows less distance covered per second. The shaded area under the curve quantifies the work done by friction. When that area is large, the book stops quickly. When small, it slides longer. Thus kinetic friction transforms useful motion into heat, reducing kinetic energy. Pause 0.8. First, place a hardcover book on the wooden table. Next, align a ruler beside the book's edge. Mark the starting point with a small dot. Release the book gently from rest at that mark. Watch it slide until it comes to a stop. Measure the distance traveled using the ruler's markings. Record the time with a stopwatch for accuracy. Repeat the trial 3 times to ensure consistency. Calculate the average stopping distance from your measurements. Use this data to discuss kinetic friction forces. Pause 0.8s first. Record the distance where the book stops. Next, note the mass we measured earlier. The normal force equals weight because the table is flat. Thus N equals m times g, with g about 9.81 m/s2. Kinetic friction Fk balances the book's momentum during sliding. We use the simple relation Fk equals mu k times N. Solve for mu k. Divide measured force by normal force. Plug in our numbers. Mu k equals Fk/m times g. This gives a dimensionless coefficient that tells us how rough the surface is. Finally, compare this value to textbook values for wood on wood. Pause 0.8 when a book slides across a wooden table. Kinetic friction resists its motion. This resistance arises from microscopic interlocking between the wood fibers and the book's surface. The magnitude of that force is proportional to the normal force pressing them together. In everyday life, knowing this relationship lets us predict how far an object will travel before stopping. For example, a heavy book on a rough table stops quickly, while the same weight on a polished surface slides farther. Engineers use this knowledge to design smoother door hinges that require less effort to open. Similarly, furniture makers select wood types with lower kinetic friction coefficients for sliding drawers. Reducing friction not only saves energy, but also extends the lifespan of moving parts. Thus, a simple book sliding experiment illustrates how microscopic forces influence macroscopic outcomes. By mastering kinetic friction, we can engineer everyday objects that move smoothly and efficiently. Pause 0.8. Remember, friction resists motion, proportional to weight via mu k. It turns kinetic energy into heat, slowing the book until it stops.